Good afternoon. So, what did we discuss in our last lecture? So, in the last lecture, we have seen how to generalize the policy gradient descent from the banded algorithm to the full RL setting, right? So, what was the formula we had? Like in the banded setting, what was the expression we had? We had some function, we had some performance metric for a policy pi, and we tried to maximize that performance metric, right? So, for example, if pi of a if pi is a policy parameterized by some vector theta, what was the performance metric we had? How do you measure the performance of a policy pi? That's the expected reward that you get for following policy pi, right? So what is the expected reward that you'll get for following policy pi? So for taking action A, the expected reward will be mu of A in the bandit setting, and this is the probability of taking that action A. And this is how we measure the performance metric of some policy pi. Then what is that we wanted? We wanted to maximize this function, right? So we were using stochastic gradient descent, right? So what was the gradient of this function? We have shown that the gradient of this function will be equal to this expected value, right? Correct. And oh, in today's lecture, what we'll do is, in last lecture, we have seen this basic version of policy gradient descent, where we just, instead of mu of A in this expression, we have just used RT as the substitute, right? RT is one sample of the reward that you get for following action A, right? So you just take action A and see what one sample of the reward, which let's say AT is the action that you took. And if you want a sample of mu of AT, what can we do? We can just take RT plus 1 as that sample, right? Whatever is the reward that you get for taking that action, you just observe that sample and substitute that instead of mu of A. So that was the basic version of the policy gradient descent. In this class, we'll look at some variants of policy gradient methods. For example, the basic version, whatever we know, is called the vanilla policy gradient method or the reinforced algorithm. This is referred to as the reinforced algorithm, which is the vanilla policy gradient method. That is what we have seen before. In this lecture, we'll see a couple of variants of it. One variant is called having a baseline. There is a variant which is called baseline uh, based policy gradient method, where we'll see what exactly that is, but that is one thing which we'll cover. And then we also look at what is called actor-critic method, and then we'll also see what is called advantage actor-critic method. Okay. So roughly these are the things we'll see in today's lecture. So first, what we'll do is we'll see these variants in the bandit setting so that you clearly understand what is the main concept. Then we'll just generalize it to the full RL setting. Okay. So let's look at these things in the bandit setting first. I think we briefly discussed these things, but let's look at it in more detail. So this is the performance metric, and this is our uh, gradient. So in the vanilla version of the policy gradient descent, which is called reinforce, what we do is we'll just look at this uh, expression like this. Like you can just write mu of A as this, right? Like you just say that AT is sample according to pi. You can just call it like this. And when AT is sampled according to this, then mu of A is nothing but expected AT given T. And we had this. So instead of writing A given A is sampled according to pi, I'm just writing it as AT is sampled according to pi. And for this, all that we want is some number which whose expectation is equal to the gradient, right? This is the exact gradient. So we just wanted something whose expectation is equal to the gradient. So what we have done is we have just used RT into del theta log phi of AT, right? Because if you look at the bottom expression, if you take the expectation of that, that is equal to the exact gradient. So that is what the stochastic gradient descent algorithm is, right? You substitute something other than you can substitute anything whose expectation is equal to the gradient. So this is the basic version called the reinforce. Now let's look at what is actor-critic version of this. So in the actor-critic version, uh, do you remember we have discussed this when we were discussing the policy gradient method, right? So what was the actor-critic version? So what change we do to this thing? Yeah. So all that we want is some like instead of mu of AT, here we are using RT, right? So RT is just one sample approximation to mu of AT, right? So instead of that, we could have looked at all the previous rounds in which let's say AT, let's say AT is equal to A. You can look at all the previous rounds in which arm A has been played and take mu bar of A as the estimate of mu of A. Instead of taking one sample estimate, you can just maintain an average of all the rewards that you got whenever you played arm A, and just take the mu bar of A instead of RT here. You just use mu bar of AT instead of RT, right? Because that also is in expectation is equal to mu of A, right? Like mu bar of AT is uh, the expectation of this will also be equal to mu of AT, right? Because that is also a sample average. So that will also satisfy the stochastic gradient descent property, right? Mu bar of AT is a random variable, right? Because it's a average of some sample rewards, what we have seen, right? So in expectation, that will also be equal to mu of AT. So we are fine with any substitution whose expectation is equal to our interested term. So this is what is called actor. Like you just maintain some estimate of generally we take the estimate to be the sample average. Okay. So what will we substitute here instead of this? We'll just substitute mu bar of 80 into delta log phi of. Okay. So this is what we'll substitute instead of the gradient, which is the actor-critic version. Okay. So when here the estimate that we'll take is the sample average. Okay. Hmm. So here, why is this called actor-critic? Do you remember? Like this mu bar of 80 is telling us how good a particular action is, right? So what is the expected reward for taking an action A? So that is like a critic, which is telling you how good your value of that particular action is. Okay, so that is generally called as a critic, which is giving value estimates. That is, it is telling how good our action is. So that is what the critic is telling, and uh, the actor is a policy which we are learning, right? So the policy is like the policy is like telling us what action to take, right? In at any given state. So that's why you call it the actor. Okay. Mm. So which tells us how to act. So here we are in the in algorithms like UCB, etc. Those are only value-based methods where we are just maintaining values. We are maintaining the mu bars for all possible A's, and we are doing something based on that. So all those were called value-based methods. And in the reinforced method, we are not maintaining any value estimates. We are just maintaining some parameters for the for the policy, and we are just updating our policy. So this is called the policy-based method. But this actor-critic version is like the combination of both these methods. We are using both value-based method and a policy-based method, right? Because we are essentially having a representation for our policy, and we are updating our policy using SGD. And for calculating the gradient, we are using a value-based method, which is like estimating what is mu bar of it. Okay. So that's why it's called a hybrid version of both policy-based method and value-based method. Okay. Is this terminology clear? Or should I repeat? Huh? No, active critic is called because of these reasons. We are maintaining a policy-based method and we are updating our actor. Actor is like a function which tells you what actions to take. So pi is the function which is telling you what actions to take. And critic is like the value function which is telling you what is the value of a particular action. Yeah. So this is like the where this like this is actor this is based policy based method because we are having some estimate of the parameterized policy and we are updating our policy, so that's why it's called policy based method. And it is also called value based method because we are also maintaining the value of every action and we are updating it over time. So mu bar of 80 we are maintaining, right? So we are updating it over time. No, maintaining a value estimate itself, because of that we are calling it a value based method. So we are maintaining what is the value for each. When we go into the full RL setting, you'll appreciate this even more. Okay. So, for example, if you recall the reinforced method that we had in the full RL setting, we did not have any value estimate, right? We had something like this, and we were just updating. But if you want to implement the actor critic version of the full RL setting, we have to explicitly maintain the estimate of the value function. What is V pi of S? We have to maintain that. We'll see that. Okay. So this is one variant. Actor critic version is one variant. There is another variation which is possible, which is called baseline. Okay. So what this baseline variation tells us is, so this is our expected. This is our gradient, right? This is the gradient which we have. Uh, Instead of using this as our gradient, let's say instead of using this, I use something else. Let's say instead of using that, we use some other value for the gradient. Okay. So this B is called the baseline. We are subtracting something from this mu of A and using that instead of using the actual one. Okay. So the what we can show is if you substitute any B which is not a function of your AT, as long as B is not a function of AT, uh, both these expressions will be equal. Okay. So generally, this is used to have some stability in the algorithm, like because we are not changing anything in the gradient, but it will give us more stability. For example, uh, if one standard baseline that is used is here mu of a t is the expected reward for taking action 80, right? So instead of using that alone, you just subtract something which is the average reward that you got so far, irrespective of what action you took. So, for example, let's say there are two actions, A and B, and let's say mu of A is like 1000, and mu of B, let's say, is 1020. So now these numbers are little larger, right? So instead of that, instead of using mu of A here, you just use mu of A minus mu of A plus mu of B by 2, so that the term which we use here will not go too high or too low. We are just subtracting the average from this. Okay. So the good thing is, even though we do that, there is no change in the gradient which we are having. But in the sample, because we don't use the exact gradient, right? We'll just use this as our gradient, right? As an estimate of our gradient. So it makes a difference in the convergence. This is what we'll use, right, as a substitute for the gradient, because we are doing the stochastic gradient. We don't even use this, we will use this, right? So what I'm trying to say is, if you subtract something called the baseline, which is not a function of your uh, action which you are taking, then the gradient, stochastic gradient descent will still, the theory of stochastic gradient descent will still hold. Huh? I'll prove that it won't change, but you agree that if I use any other function where both these terms are same, if both these terms are same, then instead of using this, I can use this for my SGD update, right? Mu of 80. No, that is not what I mean. So instead of using 1000 here, I'll use 1000 minus 1000 plus 1020 by 2. Okay. Yes. It can be any function which is independent of 80, which doesn't depend on 80. Okay. No, this will ensure that this is like the this is some general trick which we use even in machine learning, right? We try to bring the features around some particular value, right? Yeah, so it will just make the mu of 80 around zero. Like this term will be around zero. We're centering that. That's the only thing. So let me show you that first. Let me show you that both these things are equal. So this is the claim that both these things are equal if b is not a function of okay. So what is it is to show this? What is that I need to show? I have to just show this thing, right? It suffices to show this thing, right? If I show this, that is good enough to show that both those expressions are equal, right? So let's see how we can do this. It is enough to show this. So let's consider this term. So let's consider this term and let's try to do something. So what can I write this as if I want to expand this? This is like phi of a into p del theta log pi of where 80 is sampled. It's like right. So here this is what it means, right? A is sampled according to pi. So this is the value, and if b is not a function of a, if b doesn't depend on a, then I can pull that out, right, of the summation. So that will be, and this one I can write it like this, right? Right. So since b is not a function of a, I just pulled it out and I've written the remaining terms. So these two will get cancelled. So what will be left out? Like here, a means a theta, right? So what I'm left out is this, right? So is this term zero? Hmm? Why? Yeah, because you can use it's a you can bring the summation inside the derivative, and what will happen? It's like one, right? This value is one, so the derivative is zero. Fine, because it's a probability, it will sum to one if you sum over all possible values of that distribution. So, um, so what we are learning is in the stochastic gradient descent, you can instead of using RT, you can substitute any value which is not a function of your current action. Then still your expected value of that will be equal to your gradient. Okay. So generally, this a typical base, as I said, a typical baseline that is used is while updating, you just use RT minus R bar into, right. You just take this as your gradient, as the stochastic gradient. Instead of using RT, you use substitute minus R bar, where R bar is the average of all rewards, irrespective of all rewards in the sense that the rewards that you got for taking any action, not necessarily A. Okay. The sample, the average of all rewards, sample average of all rewards. So, no, this is empirically used to have good results. Like here, we are trying to just center the reward. Like although the expected, it relatively tells how good that particular action is compared to all other actions. Right? Every action will have some reward. Here we are just looking at how good that particular action is roughly with respect to all other, on an average, how good that action is compared to other actions. So it, generally, if you use this baseline, you see better convergence. Okay, like this tells how good uh, an action is compared to an average action, or compared to a typical action. You can think like. I don't know what exactly to write here, but that's what I mean. Compared to on an average, if you just take a random action versus this particular action, what is the advantage of taking this action? Because R bar is the average of all the rewards that you got, irrespective of what action you took, right? Okay. So are these two concepts clear to you? Like one variant is bringing actor-critic, where instead of substituting RT, you just substitute mu bar of AT, right? Instead of taking RT as the estimate for mu of A, you just take mu bar of A. You just look at the sample average and substitute that. That is the actor-critic version. The other thing is you can substitute any, you can subtract any value from this mu of A, as long as mu B is not a function of AT. And one typical B that is used is this R bar, okay, which is the sample average reward that you got till now, where the average is taken over the rewards that you got for all the actions that you have taken till now, not necessarily for that particular action. Okay, now we'll try to just see how these two things will look in the full RL setting. Okay, that is in the MDP setting. Okay, and so in the yesterday's lecture, we have derived the policy gradient update, right, for the MDP setting. What was that? Can you recall? Like, what was the objective we used for measuring the performance of a policy? Like in the bandit setting, that was this, right? What is the expected reward that you get for taking action A? In the full RL setting, what was the performance metric we used? Huh? Yeah, we use this. What is the value that you'll get for playing according to policy pi and starting from some state S naught? And we also assume that we had some starting distribution, right? So where because S naught can vary every time. So what we took was, let's say there is some starting distribution D from which S naught is always generated, and we just looked at what is the value for starting from the state S naught, where S naught is sampled according to the starting distribution D, right? And what is the gradient that we have derived for this uh, objective? Do you recall? So here instead of the reward, we just substituted this trajectories return, right? Starting from where tau is sampled, right? Tau is the trajectory which is obtained by following some policy phi. So instead of RT, we use this G tau, which is like the return for the whole episode, right? And then we had to just have this, and the other term boiled to something like this, right? Correct? Where tau is what? Tau is the trajectory. Okay. Hmm. So here we'll try to use this concept of baseline and get a different version of this formula. Okay. So what is G tau here? G tau is R1 plus like R1 plus gamma 2 plus gamma square RP like that, right? So I can write it like this, right? So del of J theta equal to expected value over. Hmm. So this G tau, I can just even put it inside this summation, right? Right now there is no issue. So what I'll do is I'll just write it like this. So what is my G tau? Sigma k equal to 0 to t gamma power k into rk plus 1, right? This is G tau, right? I'm just summing all the rewards with the appropriate discount factor. Okay. And into the rest of the thing will be the same, right? So here, one what we are trying to do is instead of G tau, we want to make it GT. So what is GT? The return that you get starting from time t, right? G tau is the return starting from time 0, right? Because that's the return for the whole trajectory, right? G tau. So we are trying to use the baseline trick uh, to make this instead of G tau, we can just replace it with GT. Okay. This is useful in getting to the actor critic version. Okay. So you understand the difference between G tau and GT, right? G tau is like G naught from the total return that you have from, and GT is the return that you have from time t. Okay. So that's what we're trying to do now. Hmm. So if I want to here, this is G naught, right? Like the G tau, whatever here it is, that is G naught, right? So if I want to make it GT, what should I argue? Yeah, instead of G tau, I want to write GT there. So GT is like GT has a fewer terms compared to G naught, right? So uh, and what we are trying to use is the baseline trick in the sense that uh, whether RT minus 1 is RT minus 1 a function of AT? No, right? RT minus 1 is not a function of AT, right? So that means you can think of it as the B which you have, where any you can subtract anything from your this term which doesn't depend on AT, right? So what I'll try to do is, so what I'm trying to claim is, since like if it doesn't depend on AT, this is just like any other B, right? Which doesn't depend on AT. What can I write? I can write like this, right? I will just I have just showed you this thing, right? You can use any B, and whatever B you use, if it doesn't depend on AT, then this is true for all k less than t, right? We have just proved above, right? That you have this expression, you take this expression for any B which doesn't depend on AT, that value will be zero. That's what we just showed. Here we are trying to, I'm just stating that again, like with the RK, right? RK doesn't depend on what AT is for k less than t. So the expected value of that will be zero. Where this is not GT, this is G tau 1. Yeah. Like I just substituted this thing. Okay. So is everyone clear with this argument? Like for any B which doesn't depend on AT, I just showed that this term will be equal to zero. I'm just using that result now. Okay, from the baseline proof. Our baseline proof implies this, right? So now using this, how can I write my this thing? Expected value sigma, because in this expression, all the terms uh, which involve the rewards up to time t minus 1 will vanish because of this thing. So what I can write is just the remaining terms. Like this will imply this. Okay. Fine. I'm just changing the summation index. Instead of looking from k equal to 0, I'm just looking it from uh, k equal to t. Okay. That's all I'm changing here because of that. Because of this rule. Okay. So what is this equal to? Is this equal to GT? Is this term equal to GT, or any minor change is required? Yeah, to just pull some gamma out, right? So what is that equal to gamma power t into, right? I just pulled gamma power t out. Okay, is this fine? Yeah. Okay. So this is what gamma power t into gt. Then now, okay. So generally, this is the expression that you'll see in the book. So this is one way to derive that expression. Like, uh, so I like you don't see the g tau notation in the book, but to come up to this expression, I found this is a good way to explain. You just think of the analogy with the bandits and just derive the g tau based expression, and then use the baseline trick to come up with this version. Okay. So Uh, the more general version, generally there is a theorem called policy gradient theorem, which essentially tells you this thing, like the policy gradient is equal to, so instead of GT, they have, you can even derive the following. Okay. So this, generally this is what is a more popular expression which is derived. We can show that in general, the policy gradient, if you take that particular objective, then the gradient will be equal to this. This is the one which you can mostly remember. And by looking at this expression, you can derive different variants of the policy gradient algorithm. Okay. So this expression is generally called the policy gradient theorem. Okay. So from we'll take this expression as our base expression and try to derive different variants of the policy gradients. Okay. So first of all, so this so the basic version, as we called, is the reinforced algorithm, right? So if you just look at this, yeah. No, I did not show that here, but generally this is a theorem which says that for the given objective, this is the thing. But it's easy to see why this comes from here. Why? Because let's say this is the expression that you have to substitute, right? This is the main expression which you have inside, right? Now, we can use the concept of stochastic gradient descent, which tells us instead of using this exactly, you can substitute something whose which in expectation is equal to this term, right? So if I take GT is what? What is Q pi of STAT? Expected value of GT for being in status and taking action AT, right? For following policy pi. So you can think this as an estimate of q pi of st comma at. If you take this as the starting point, it's very easy to see why you can use gt instead of q pi of st comma at. Because if this is a theorem, then you are just taking some. If you just substitute gt here, that is like the stochastic gradient version, right? You can substitute anything whose expectation is equal to your gradient value. So if you start from this, if you take gt, that will give you the basic policy gradient algorithm. Is it clear? So the first variant, you start from this, you just keep looking at this term. If we, based on this term, by doing different things, we'll get different variants. Like the first thing is reinforce, where you use this relation between the q pi and gt and just take this as gt, which is like an estimate of q pi. Gt is an estimate of q pi stat, right? So that's why in the basic reinforce algorithm, this is what we use. Okay. The next variant that we'll see is the reinforce algorithm is also referred to as Monte Carlo based policy gradient method, because to estimate what is q pi, you are just looking at one episode and taking that estimate as q pi. Okay. Then the second variant is Actor-Critic. So can you tell me now, that you have seen this, how we went from this thing to the reinforce? Can you tell me what will be the Actor-Critic version? So instead of having q pi, I just used gt. That became our reinforce. Right here we had q pi. To estimate q pi, I just use one sample return. That is our reinforce algorithm. Now, what could be the Actor-Critic version? Instead of gt, what could I have substituted there as an estimate of q pi? I can maintain what is I can maintain what is q pi, right? So, for example, I can maintain what is q pi stat with some weights w. I'll maintain an approximation for what is q pi stat, right? Which is like a function approximation for q pi. Is this clear? Like how we had instead of mu of a in the basic policy gradient method, I just used RT, right? Which is one sample of mu of a. The other, what was the thing that we used in the Actor-Critic version as an estimate for mu of a? We just use mu hat of a, right? What, for example, mu hat could be the mu bar which you have seen. Similarly, uh, we are trying to substitute some estimate of q pi. So one good estimate is you just do the entire trajectory and see what happens. What is the return that you get? That is like GT. Like the analogous thing is GT here, right? Because that is the expected value of GT is what is giving us the Q pi. That is one thing. The other thing is you maintain some estimate of what Q pi is. What Q pi is. So that you'll learn not just based on your current GT, but you'll learn using whatever approach you want to learn, right? You would have, let's say, you are interested in what is the sample, what is the estimate for q pi of s comma a, q pi hat of s comma a. Then we have learned different ways of finding this, right? For example, you can maintain a neural network and keep updating your thing based on some. We have looked at TD based approximation also, right? You just approximate q pi using some linear function, let's say, and you keep updating your weights as the which will minimize the mean square error, between what exactly q pi is and what your estimate giving us. So maybe I'll just show you that. Since so all that I'm saying is just don't rely on your current episode for estimating what q pi is. You can just so for example, let's say you want to estimate what v pi is. We have seen, right? You can just maintain some linear function approximator. Let's say you want to estimate v to be some linear function approximation like this, and we want to find what this is the true value of v pi, and we are maintaining an estimate. You learn some good weights which will represent your v pi. So for that, we have looked at multiple ways of doing that, right? Since we don't know what exactly v pi is, one way is you just use TD based method for exact v pi, which is the current reward plus the estimated future reward. Or you could use this kind of thing. So all that I'm saying is just don't use the current trajectory and calculate what GT is. You keep learning what v pi is based on all the information that you have till now, and keep having some estimate of what v pi is, and use that estimate instead of just one sample return. So that's all I'm saying. Instead of using q pi here, because we don't know q pi, one way is just take one sample return and use GT. The other way is you maintain some estimate of what you think as q pi is, and keep updating it through whatever information you have about it, and substitute this value instead of q pi. So what will be your gradient here? Like instead of this is the gradient we had, right? So instead of q pi, we are substituting q pi hat, which is an estimate of what q pi is, and the rest of the thing will be the same. So now you understand what is actor critic more clearly, right? So this is like the critic. We are estimating what is the critic. So the critic also we have some parameters. What is W, right? W are some parameters which is representing what your critic is. For value function also we have some weights W's which you are trying to estimate. And for policy also we have some weights, right? What which are thetas. Thetas also we are learning on the go, and these W's also we are learning on the go, right? Based on whatever interactions you are having, you will see some episodes, right? So using those episodes, you learn what is Q pi. That is, you learn what are W's, and you also learn. You also keep updating your thetas using stochastic gradient descent, where this is the gradient which we use. Okay. So here Q pi hat is the approximate estimate of Q pi. So as I mentioned, it's good to remember that we are dealing with two sets of parameters here. One set is called, there are two parameters, two sets of parameters. One set of parameters is called theta, which are like the actor network parameters, which deal with policy. And we have another set of parameters, W, which deal with the critic network parameters, which deal with the value. Okay. Is this fine? So you know the update rule for theta, right? The update rule for theta is theta nu equal to theta old plus some small constant times this one. That is your update rule for theta. What will be your update rule for W? How do you learn W? Just now I have shown, right, how we are learning V pi of S, like V hat of S, right? Similar to that. You just keep updating your W's based on whatever rewards you are seeing. Okay. That will be very similar to what we have seen in the value function approximation setting, where we are learning how Q star we are learning, or how V V V pi we are learning, right? For example, you can take it as a linear function of the weights W and keep updating your W's using the semi-gradient methods which I have discussed before. Okay, so maybe I'll try to show you the exact algorithm maybe in the next class so that you will understand what exactly the update rule is. But at a high level, you understood, right? Instead of substituting GT for Q pi, you are just maintaining some estimate of what you think is Q pi and using that estimate, which will be a better estimate of Q pi rather than just using one sample written. Okay. So this is at a high level what actor critic version is. Then we'll also look at what is called advantage actor critic, which is called A to C. So here, instead of using Q pi here, like this is the main expression which we had, right? Q pi into this del log pi. Instead of Q pi, what we'll substitute is in the reinforce we substituted GT instead of Q pi. In the actor critic we substituted Q pi hat. Here what we'll substitute is something like called advantage function, which is same as what we have seen in the baseline. In the baseline for the bandit problem, what did we substitute? RT minus R bar, right? Which is RT is the reward that you got for taking action AT, and R bar is like the average reward that you get. So similar to that, what we'll have is, as I told you, that you can think of RT minus R bar as like the value of some particular action compared to a typical action or an average action, right? So RT is the reward that you got for taking action AT, and R bar is the reward that you got for generally for which is an average over all actions. So how much good action A is compared to a typical action? That's what we are trying to write here. Similarly, the advantage function is defined as Q pi of STAT minus V pi of ST. Okay. So Q pi of STAT is for taking action AT and then following policy pi, what is the return that you get, expected return that you get. And what is V pi of ST? You just follow policy pi. Policy pi might not tell you to take exactly this action AT, right? It will tell you some, with some probability, it will tell you different actions. So now you're looking at what is the difference between what gain you will get for taking action AT versus some random action according to the policy pi. So this is like the average of all possible actions, right? What you can write this as? You can write this as expected Q pi of S comma A, where A is according to pi, right? That is what V pi of ST, right? This is the definition of V pi of ST, right? V pi of ST is what? Q pi of ST comma A, where you take the average of that, where A is sampled according to pi. Do you agree with this? So this is like what you are trying to measure how good action A is compared to an average action. If you take some action at random from some policy pi, what is the value that you will get versus what is the value that you will get for taking this particular action AT. That's why this is called as the advantage for advantage of action 80. So here the good thing is this doesn't depend on what 80 is, right? This term doesn't depend on what 80 is. So this is like the baseline. This is like a baseline which is independent of what 80 is. Because it doesn't depend on what 80 is, it just depends on what ST is, right? Given ST, I can tell you what is V pi of ST. I don't need to know what is 80 to tell this. So that's why this is a baseline. So that's why we can use this because adding this term will not change your gradient as we have discussed before. Correct? This is like 1B which you can have and this will not change the gradient because it's not a function of 80. So this is the definition of uh, this is the definition of what advantage function is. So you can treat this as baseline and which is equal to this. This is equal to this. And since V pi of ST doesn't depend on right. So the update rule is essentially this. You just use this. Okay, this is what we'll use. Instead of using Q pi, we'll just use A pi. So for A pi also, what we can do, we can just keep an estimate of what A pi is. So one way that you can do is you have three networks. One is the policy network, which has the parameters theta, and you can also maintain a Q function. Let's say it has a weight W, and keep estimate of what Q pi is. If you want, you can maintain one more function approximation for V pi, which will have some other set of weights. And you keep learning what is a good estimate for Q pi, what is a good estimate for V pi, and based on that, you calculate what A pi is, and you can use that here. Okay, but you understood why is this a baseline, right? Because all that we want is some function, something which is not a function of 80, and it is also similar to this thing like RT minus R bar thing, right? Here this RT depends on what 80 is, and R bar is like what an average action, the reward of an average action. Similarly, here Q pi of ST comma 80 is the average return that you get for taking a particular action 80, and this V pi of ST is like the average return that you get when you take a random action according to policy pi. So this difference will tell you how whether A is how much advantage that A has compared to a typical action in policy pi. So if this is negative, then you can think that the action is not good. If it's positive, then you can think the action is good. Okay. So this is what is the actor critic. Sorry, this is the advantage actor critic. So it's it's actor critic. It falls under actor critic because we are still maintaining some value estimates and we are doing the policy gradient, and we are calling it advantage actor critic because we are using this difference as the. So you can think of this as actor critic with baseline, right? Mm, Yeah, roughly, these are the concepts that we have for today. So, they'll be different only, right? Yeah, because you can model QPy as some linear function, let's say, of S comma A, and you'll model VPy, let's say, a linear function or neural network, whatever you want. It will take ST and give you VPy of ST. Yeah, you can also maintain one network which directly gives you API also. Maybe. Actually, there are some. I think maybe in the next class I'll show you one minor modification that you'll do for this, so that you'll maintain only one network instead of maintaining two networks, like one QPy, one VPy. Instead of that, we'll just maintain one network. And so this, because that is roughly based on this what is called the TD error. So if you look at this, what you can write this as, you can write this as RT plus 1 plus gamma times VPy of ST plus 1, right? This QPy you can write like this, right? RT plus 1 plus gamma times VPy of ST. If you look at it, then if you just maintain even VPy, you can calculate this roughly, right? So this is the like even with VPy, you can roughly calculate this. So based on this concept, you can use only one network as well, which is maintaining VPy. Okay. So let me see if I have the book here. So maybe once you do the assignment related to this, maybe you'll get more clarity on this. So as I said, in this is one variation where instead of maintaining separate Q and V, here they're looking at this, right? So this is like the advantage, right? Which is this is like the Q and this is V. Q minus V is like the advantage here. So here they're maintaining two networks. One is the policy network, which has the parameters theta, and the value network, which has some parameters W. And um, based on whatever experience they're learning, they're doing two things. One is, like as I said, this is a policy update which you have seen. The policy update is what? Theta nu equal to theta old plus some small constant alpha into here a pi we have to write, right? A pi is this, right? The advantage, which is the Q minus V. Q you can write it as R plus gamma into V of ST plus 1. Like S dash is ST plus 1. S is your current state. So here you are learning, you are updating your theta based on that. And your W's you are learning based on the semi-gradient method which you have seen. In the function approximation where we are learning W's, your new weight will be the old weight plus some small constant times the uh, gradient, right? So that's what we are doing. Okay. So maybe I'll try to see whether I can give an assignment on this so that you'll understand the steps more clearly. Okay. And this is the basic policy gradient method where you're just getting one whole episode of data before you take any update. You just run one episode and calculate the GTs, and then you update. This is with baseline, where with baseline you can do with actor critic or without actor critic. Like with instead of using Q, you can use G also here if you want. Because for QPy, you can also use G as your estimate, right? So there are many variants, but all these variants essentially boil down to those two concepts. Like instead of substituting R, you substitute R minus R bar, as long as whatever R minus B, as long as B is independent of AT, you can do whatever B you want. That is one concept. The other concept is instead of estimating using sample return, you maintain your own estimate. Whatever, there are different combinations of the algorithms, but all these algorithms essentially depend only on these two concepts. Instead of using RT for mu bar A, you just have RT for mu of A, you have mu bar of A. And instead of using RT, you just use RT minus B. So you can play with these combinations to get different ways of implementing this algorithm. Okay, thank you.